Good morning, everyone, and welcome to the National Biodiversity Web Teach-In Series. This morning, we have Arthur Malm from the Friends of the Fox River. This presentation is sponsored by the Community-Led Environmental Action Network in the Elgin area, or Clean Elgin. CLEAN is focused on advocating for policies that implement sustainability practices in School District U46. This includes fostering a community that understands the importance of sustainability and actively works to improve our shared quality of life. This growing organization is excited to provide opportunities for residents and students to engage in environmental initiatives throughout the Fox Valley and beyond. If you want to get involved or if you have any questions, please reach out to us at elginclean@gmail.com. Okay, Arthur, I'll turn it over to you. Thank you very much for being with us this morning.
Thank you very much. Today let's see if am I sharing my screen right now?
It is not shared yet.
Okay. Now do we have it? Does it say mysteries, models, and
yes, there it is.
Okay.
You're ready to go.
Today we have two real-life stories about the Illinois Fox River, our Fox River. Mysteries, if you will. We'll call this program AQCSI, Fox River Valley. There will be two cases in this special double feature. In the first case, we will appear with new evidence before you, the jury, in the court of scientific and public opinion, asking you to drop future charges against phosphorus for algae pollution, sludge deposition, and riverbed oxygen starvation in the Fox River. We will call this case Sestonic versus Benthic. In the interest of full transparency and for the benefit of the court, much of the data the defense uses in Sestonic versus Benthic will be made available to the jury for their future reference and analysis. The second case is from the viewpoint of a young detective looking into an old cold case involving the disappearance of an entire family from parts of our Fox. It's the case of the missing poison. Hear ye, hear ye, hear ye. This is the Court of Scientific and Public Inquiry, now in session and will not rest for the next 30 minutes. The crime, offensive conditions, a violation of Illinois Administrative Code, Title 35. The water of our Fox shall be free of offensive conditions, including bottom deposits, algae growth, and turbidity other than of natural origin. I'm not an attorney and only fake one on Zoom court, but in a random survey of 563 registered Fox Valley voters, nearly half believe our river is polluted and therefore in violation of Illinois law. Let me describe the crime scene. Our Fox River watershed was formed between two lobes of the Great Wisconsin Glacier 25,000 years ago. Our Fox travels 223 miles south from Colgate, Wisconsin, to its confluence with the Illinois River at Ottawa, southwest of Chicago. Waters at the top of our Fox in Colgate fall 450 feet towards the ocean before the Fox joins the Illinois. Those waters won't drop another 450 feet until they reach the Gulf of Mexico. It's 1835 and James Gifford, an early American entrepreneur, arrives in the Fox River Valley. Gifford tells us why the Potawatomi Indians chose the Fox River Valley for their home, describing the Fox as the finest stream he'd ever seen, waters pure with abundant fine fish. Through Gifford's eyes, we see what the Fox was, and it gives us a view what our Fox might become once again. Our biological resources are substantial in the Fox River Valley. The habitats in our creeks and our wetlands are home to a number of endangered species. Nearly 2/3 of our entire watershed is agricultural. The middle third is urbanized. In the 1800s, into the early 20th century, the Fox River Valley was its own commercial and industrial center. With a 10-fold population growth since that time, the central Fox River Valley is now the western extension of the Chicago metropolitan area. Our Fox River has had a long history of water pollution. In the late 1800s, young industries grew unchecked and pollution was the norm. Our Fox was everybody's sewer. Acid waste from metalworking factories, milk waste, brewery waste, sewage, clots of sewage floating along its surface, cattle getting sick from it. Ice harvested from the Fox at Elgin declared contaminated and unfit by the Chicago Health Department. Large quantities of organic waste with lots and lots of nutrients, nitrogen and phosphorus, were poured into our river. For over 100 years, the people of the Fox River Valley have invested time and money to reverse the pollution damage done to our Fox. Sewage treatment plants built and rebuilt over the years are only the tip of the iceberg of efforts made on behalf of our Fox. Contamination from pesticides and PCBs are nearly gone from its waters and the flesh of its fish. And sections of our Fox where the Fox runs free has some fine fish to be caught. According to Illinois, our Fox shall be free from deposits, algae growth, or turbidity of other than natural origin, but along many segments of our Fox, we see sludge beds covered with algae. In places where dragonflies, the bald eagles of the aquatic insect world, used to live and bring smiles to our faces, those are now host often to Those are often hosts to pollution-tolerant midge flies, bred in an oxygen-starved environment of muck. They live in the muck for months and then rise for a few days in mating swarms to get stuck in your teeth and hair and eyes as you walk or bike along our river's edge. 3 days, they rise, they fly, they mate, they drop their eggs, and they die. They don't even eat. We have as our crime a violation of water quality standards involving turbidity, algae growth, and oxygen-starving bottom deposits. This is AQCSI, Fox River Valley. We need to find the perpetrator. Let's investigate. Algae 101. Algae plus nutrients plus time and sunshine mean more algae and eutrophication. The apparent unnatural addition to our Fox causing the violation, it must be nutrients. And when you have a case of eutrophication, the first suspect you always lock up is phosphorus. That's been good crime fighting practice for the past 50 years. But we have an innocent until proven guilty culture, and there's new research data just out. The accused must have its day in court. We will indict this suspect, phosphorus, for crimes of the Fox River Valley and give it the fair trial that it deserves. We now have the crime scene, and a venue. Phosphorus has a long reputation for being an algae bad boy, causing turbid eutrophic waters, smothering, then asphyxiating the natural benthic habitat. We have our accused at trial. You are the jury. I'll play the defense attorney, so let's move forward. Phosphorus has been indicted for causing turbid waters with algae blooms and suffocating bottom sludge in our Fox River. And I'm here in its defense to demonstrate to you, the jury, phosphorus is not guilty on all future counts. Let me introduce the accused, phosphorus. Algae, nearly all life in fact, needs phosphorus for its energy chemistry. Rich mineral content in some waters provides an excess of phosphorus, so its presence has no bearing on algae growth. But in some waters, the availability of phosphorus limits algae growth. That's why phosphorus is often implicated in cases of eutrophication. Now together, we'll consider each of the 3 counts of the indictment. Count 1, turbidity. Since ours is a science venue, the defense will attempt to support the hypothesis that if algae is not the principal cause of high turbidity in our Fox River, then phosphorus cannot be found guilty of this charge. First, what is turbidity? To understand the crime, you have to understand the measurement. Turbidity is not color. Turbidity is pretty much the inverse of clarity. It's the measure of a liquid's ability to scatter light with a standard way to measure that scatter. To understand the crime, you have to understand the measurement. Here are 4 jars with different turbidities as measured in the world standard formazine nephelometric units. We see the jar with 50 FNUs on the left. It looks clear enough to drink. For that 1,000 FNU jar on the right, you might pay $7 at Starbucks. Now we need to understand chlorophyll A. Chlorophyll A is the near magic photosynthesis engine. Makes up about 1% of the dry weight of algae. Since we can't filter, dry, and weigh algae in real time, we measure instead chlorophyll and estimate from that measurement the amount of algae in the river. How's that done, you ask? It's quantum mechanics magic. A water quality monitoring instrument package, we'll call it a SOND, was located just above the Stratton Dam south of McHenry, Illinois at river mile 97.7. Chlorophyll A, turbidity, and a number of other water quality parameters were measured there every 15 minutes, 24/7, from late July to late October 2020. This is a scatter plot of chlorophyll A and turbidity recorded by the probe. On the horizontal axis is chlorophyll A. The associated turbidity level is graphed on the vertical axis. We can see almost all the time that turbidity is less than 50 FNUs. Water looking clear enough to drink. We can also see when turbidity was high, say above 50 FNUs. It didn't matter if there was a little chlorophyll or a lot. We'll mark that Exhibit 1. Let's look at the chlorophyll and turbidity data in a different way. Here's a plot of turbidity and algae plotted against time. The survey period from July 22nd to October 22nd. Algae is green and turbidity is red. Look at the turbidity spike around July 24th. The late July algae bloom in green dots begins days before the red turbidity spike and it ends many days afterwards. If algae was the cause of high turbidity, then the widths of both the red and green spikes would match. The 3-day long turbidity spike would have to be 2 weeks long to match the length of the algae bloom. This data also shows that high turbidity occurs with low algae and low turbidity with high algae. The two are largely independent. We'll mark that Exhibit 2. And then the defense attorney turns to the jury. If phosphorus causes algae growth and algae growth causes turbidity, then you can argue phosphorus causes turbidity. But as we've just seen, algae doesn't necessarily cause turbidity. So if you can't blame algae for turbidity, you certainly can't find phosphorus guilty either. Phosphorus, even if it does cause algae blooms, isn't the cause of turbidity. Misquoting from another famous trial, if the data doesn't fit, you must acquit. Count 2, algae blooms. Phosphorus stands indicted of causing excess algae growth in our Fox River. What say you, defense attorney? Defense attorney stands up and says, phosphorus is not guilty, Your Honor, of count number 2. Algae growth is not controlled by phosphorus in our Fox. Well, since this is AQ SCSI Fox Valley, before we cut to the data center, we'll go to the kitchen and look up the recipe for algae. The Redfield ratio recipe tells us that the typical algae cell has about as much phosphorus in it as chlorophyll A, about 1% of its dry weight. Now we'll go to the computing center. For well over a decade, the members, volunteers, and consultants for the Fox River Study Group have gathered field data to create and calibrate a computer model of our Fox River. This model was designed to answer this very ecologically and important question. During the critical summertime low flow periods, what can be done to reduce excess algae levels and the resulting damage they do to the aquatic environment? This model was built using 2 software platforms. One, hydrogeometeorological platform, HSPF, and Qual2KW, a biochemo, physio, etc. model created by the University of Washington. The University of Washington, incidentally, hosts the most important COVID-19 models on the planet. The result of this effort is a calibrated and operational model assembled and modified by the study group's consultant, Geosyntec. And what do the latest model runs tell us about algae and phosphorus? The horizontal data is our Fox River graduated in river miles. On the far right, river mile 0 is our Fox's confluence with the Illinois. On the far left is river mile 100, where the model initiates. River mile 100 is just south of the chain of lakes. Elgin is downstream at river mile 71, Aurora around river mile 45. Again, river mile 0 is the confluence at Ottawa with the Illinois on the far right. The left axis is phosphorus, concentration 0 to 1400 micrograms per liter. This graphic is a summary of 3 model runs using summertime low flow conditions and predicts river phosphorus concentrations in 3 related scenarios. The question posed to the model was, what would happen if phosphorus levels entered upstream from the north, near river mile 100, and were reduced by 50 and 75% at that location? The black line shows us the base case, the phosphorus levels expected if we did nothing. The red and green lines show 50 and 75% phosphorus reductions respectively, coming from Wisconsin and the chain of lakes. Remember, the model gives us the average of all conditions expected along the river during the growing season. As we travel down the river, we see phosphorus levels rise, picking up tributaries like Cotton and Crystal Creeks, in communities like Cary and Algonquin. Then, near River Mile 70, we pick up Elgin, and the phosphorus concentration jumps to 50 micrograms per liter. As the river continues south, we see the relatively large phosphorus reductions from the north don't seem like such a deal, because by the time you reach Aurora, the 75% phosphorus reduction is now only a 6% reduction. And the defense attorney turns to the jury and says, so if algae populations were dependent upon phosphorus availability, what will the model tell us to expect the predicted algae curve to look like? Would it be shaped like this? Would it go up like the green dotted line, telling us more phosphorus available, the faster the algae will grow? Or would the algae curve look like this, as it rises and falls using the phosphorus available, and shape something like the green dotted line shown here? If phosphorus caused algae blooms, then we would expect the shape of the algae curve to somehow relate to the shape of the phosphorus curve. But that's not what we see. The model shows neither. Algae almost flatlines. The model is telling us, as far as algae is concerned, it doesn't really matter how much phosphorus there is in the river. If anything, the model tells us if we want to control algae in the southern Fox, control it before it reaches River Mile 100 in the north. That's pretty much all that matters. The shape of the algae curve shows little, if any, resemblance to the phosphorus curve. And if the shape doesn't fit, you must acquit. And we'll call that Exhibit 3. Looking at this scenario a different way, we can see a fourfold increase in phosphorus causing only a 30% increase in algae. If phosphorus was causing algae growth, you would expect more than a 30% return for a 400% investment. We'll call that Exhibit 4, which reminds us that algae levels in the Fox appear more dependent upon their initial populations than the phosphorus levels in the river. Let's review count 2. Are algae blooms in our Fox caused by phosphorus? No. Algae levels do not change in a manner that correspond with the increase in phosphorus levels across our watershed. Phosphorus must be acquitted of charge 2. Is there anything else happening in the model that we should be paying attention to? Well, yes, there is. Because then the defense attorney for phosphorus continues, because this graphic predicts reducing phosphorus at our wastewater treatment plants causes an increase in benthic algae. Amber says, what? Oops, different program. That's better. We'll call this Exhibit 5. And the courtroom turns to bedlam, and reporters go rushing out to file their news story with a headline, "Reducing Phosphorus Increases Algae." The judge calls for order in the court and then introduces the third count. Phosphorus-induced algae is the cause of sludge and bottom deposits with resulting benthic oxygen starvation. The defense asked for a brief recess, during which we'll get some background. So as it turns out, there are two basic types of algae, those that stick to stuff on the bottom and those that don't. The kind that sticks to things on the bottom are called benthic algae. The ones that don't and float downstream suspended in the water column are called cystonic algae. Cystonic algae have little adjustable personal flotation devices called gas vacuoles to keep them from rising all the way to the surface or sinking down to the bottom. The sampling method you use determines if you're measuring cystonic or benthic algae. In the left picture, you see a water sample being taken for lab analysis. It measures algae in the water column, cystonic algae. In the middle picture, we see an instrument sonde tied to a float. The sonde also measures algae in the water column, cystonic algae. But the picture on the right shows our researcher from Deutschler Engineering scraping algae off the bottom rocks. That's benthic algae. Both cystonic and benthic algae make oxygen by day and consume oxygen at night. So the defense attorney has returned with defense hypothesis number 3. Phosphorus is not the cause of sludge and bottom deposits. The cause is benthic algae, silt, and other detritus on the river bottom. But there are some differences between there are some differences between benthic and cystonic algae in the Redfield recipe ratio, but they're likely pretty close. The differences I see between cystonic algae and benthic algae is when cystonic algae needs more phosphorus, it has to use whatever phosphorus is floating downstream alongside. Benthic algae, on the other hand, anchor themselves on the bottom, kind of like customers at the counter of a sushi station, sitting and watching an endless conveyor of fish and other nutrition passed by. The Qual2K model projects the growth and decay of both cystonic and algae for every phosphorus control strategy it calculates. This graph predicts the result of reducing wastewater treatment plant phosphorus discharge to 1 milligram per liter, about a 75% reduction for each of the plants. The result predicted is a near uniform phosphorus concentration of 200 micrograms per liter along the entire length of the river. And as we saw before the recess, the result of reducing phosphorus in this scenario is an increase in benthic algae along most sections of the river. We can see the predicted consequence, benthic algae growth, the red dotted line, over the baseline downstream of River Mile 60. The vertical axis, algae per meter squared. The model is clear. Reducing phosphorus is likely to increase benthic algae. And if we look back at the previous scenario, by reducing phosphorus upstream of River Mile 100, the increased benthic algae growth extends the entire length of the river downstream. How can this be, you're thinking to yourself? Reducing phosphorus pollution increases algae pollution? How does the model explain that? Well, it appears that cystonic algae throws a bit of shade. Any reduction in cystonic algae allows more sunlight, evidently of specific wavelengths, to reach the bottom, helping the benthic algae grow. This graph shows that by reducing phosphorus, the oxygen deficit problem in parts of the river actually becomes worse, not better. The more phosphorus you remove, the more benthic growth you have, and the lower the nighttime oxygen levels predicted. That's going in the wrong direction. And we will mark this Exhibit 8. The model predicts that by reducing upstream phosphorus, you will increase benthic algae and worsen downstream nighttime oxygen levels with a potential for more benthic asphyxiation. And then the attorney for the defense of phosphorus stands up and asks, how can my client phosphorus be charged with bottom deposits or benthic oxygen starvation when the model says more phosphorus means less of each? Model schmodel, we hear in the murmurs throughout the courtroom. Is there any actual proof benthic algae also causes oxygen starvation? Well, we know from many studies, the dissolved oxygen problems of our Fox are nearly always behind its dams, where sand, silt, leaves, branches, and benthic algae settle to become what is known as detritus. Detritus is kind of like aquatic lasagna, with alternating layers of silt and algae and leaves and bacteria that build up over time. In fast, free-flowing sections of our Fox, like this section at River Mile 79, just downstream of Algonquin, we placed a river sonde equipped to measure chlorophyll and dissolved oxygen. On a typical week, the green line shows nearly constant cystonic algae populations, and dissolved oxygen levels in brown show the sun went up and down 7 times that week. Let's make sure we understand our dissolved oxygen measurement. Oxygen has limited solubility in water, around 10 milligrams per liter, depending upon temperature. Oxygen is required for a natural high-quality river habitat. Some species compete for oxygen more effectively than others. Oxygen can be added to the water by natural turbulence at the surface, or oxygen can be added to the water by photosynthesis. And oxygen is depleted from the river water by respiration of algae, bacteria, and the full range of aquatic species. So in this 3-day view of our data, we see oxygen concentrations rising in the morning with the sun and setting in the evening as photosynthesis turns off and on in this free-flowing stretch of the river that has plenty of natural water turbulence and a rock bottom. In contrast to the rock bottom at River Mile 79, the slow-moving waters behind the dam at River Mile 77.2 has aquatic lasagna for its bottom. To learn how that lasagna can impact oxygen on the bottom, a sonde was set with 2 chambers. Basically, benthic oxygen demand, aka sediment oxygen demand, is determined by filling 2 containers, one clear, one black, with river water, and placing those containers upside down over the river bottom. Anything in the water or on the river bottom is trapped. Both containers have recording oxygen probes. The only oxygen available in the dark containers is that originally in the water column. The clear container has its initial oxygen, but also lets in light, and with the light allowing algae trapped inside to photosynthesize and make additional oxygen. This was a 24-hour test. The brown line is the dissolved oxygen concentration in the dark container. We see oxygen levels starting just over 8 milligrams per liter, then dropping to near 0 during the course of the day. In the clear container, the green line, we see algae photosynthesizing and maintaining oxygen levels pretty well until the sun goes down. What you, the jury, will find important is not so much the green line, but the slope of the brown line. I'll call this the benthic deoxygenation curve. We know from river water sampling grabbed during the study, the 5-day biological oxygen demand of the river and its sestonic algae was consistent and in the neighborhood of 5 to 7 milligrams per liter. That test, known as BOD5, is also a black bottle test allowing no photosynthesis. As oxygen demand over 5 days of 7 milligrams per liter is a deoxygen rate of 1.4 milligrams per liter per day. I've graphed that deoxygenation rate of the river in gold. The deoxygenation rate above the lasagna on the bottom is 17.25 milligrams per liter per day, 10 times faster than the river with its sestonic algae alone. Ready? We'll call this Exhibit 7. And when we look at the sestonic algae and dissolved oxygen data recorded by our sonde behind the Stratton Dam pool, what we see is sestonic algae in green and oxygen in brown, and how these levels changed over the 3-month period. On the left in late July, we see a sestonic algae bloom with nighttime oxygen levels dropping to near 0. But look what happens in August. Even though sestonic algae levels improved, nightly oxygen concentrations got significantly worse, falling to 0 on a daily basis. This is real data that is showing asphyxiation, not only at the river bottom, but the entire nighttime water column. We'll label that Exhibit 8. And now, with real data in hand supporting the computer model projections, the defense attorney rises for a final time to address the jury. There's been the common belief that the more phosphorus that enters our river, the worse the algae becomes, the more sludge on the bottom, and the more asphyxiation of the natural riverbed ecosystem. That is count 3 against the defendant. But the best available science shows something very different. Lowering phosphorus levels may act to increase oxygen suffocation in our river. The lasagna of benthic algae and detritus in areas behind our dams exert over 10 times the oxygen demand of the rivers flowing above, the river water flowing above. The defense of phosphorus attorney continues, according to the data and model projections, oxygen levels will not improve with reductions in phosphorus, nor will sestonic levels be significantly changed from where they are today. And while there's plenty of good work I had necessary to restore our fox, there's no factual basis for concluding that further reducing oxygen concentrate or phosphorus concentrations will relieve bottom deposits or benthic oxygen starvation. Our best efforts to date, to the surprise of most of us, suggest that even the reverse may be true. And with the fact-based support of new data and modeling, you must acquit phosphorus of count number 3. Phosphorus-induced algae growth is not the cause of bottom deposits and benthic oxygen demand. Rather, benthic algae, silt, and other detritus, not phosphorus, are our villains that must be arrested and put down. And now we take the case of cystonic versus benthic to you, the jury. The crime reflects the public recognition of the offensive conditions in our fox. Phosphorus is charged with a 3-count crime causing turbidity, algae growth, and bottom deposits. We've seen how algae levels and turbidity are largely independent. So even if phosphorus did cause increased algae growth, there's no basis to conclude more phosphorus causes more turbidity. You must acquit on count 1 because we've shown cystonic algae, and thus phosphorus, does not cause excess turbidity. We've seen changes in phosphorus levels do not result in corresponding changes in cystonic algae populations. The Qual2K model predicts a complicated relationship where reducing phosphorus has little, if any, impact on cystonic algae and may have negative ecological impacts. If reducing phosphorus doesn't improve algae conditions in the river, you must also acquit on count 2. And we've seen how bottom deposits and benthic oxygen starvation are not due to phosphorus levels, but due to the aquatic lasagna of benthic algae, silt, and other detritus, especially in areas behind our fox's dams. Since these conditions are not linked to phosphorus in our fox, you must acquit on count 3 as well. But before the defense finally rests its case and gives it to you, the jury, to decide, we must add a final comment. There is no question phosphorus is an important contributor to eutrophication in many lakes and rivers of our country, as well as the infamous dead zone of the Gulf of Mexico. And while these statements are both true about phosphorus, this new data suggests additional phosphorus control will not be successful in solving our Fox River's reputation as a polluted river. Rather, ours is a clean river with clean water and a dirty bottom, and the removal of its obsolete dams, restoring natural river hydrology and biology, remains the clear, apparent solution to our Fox's issues with algae pollution, benthic deposits, and localized sludge deficits. So before part 2 in this special presentation of AQSCSI Fox River Valley, I'd like to address the teachers among you for 120 seconds. So we'll start the clock here. Okay, everybody else watching live can get up and run around the house. So in the framework for science education teaching standards, they look to identify practices and cross-cutting concepts used to address and solve problems of science and engineering. When the teach-in asked me to present today, the Fox River Study Group had just released the first public data from their 2020 studies and the modeling that was just used in cystonic versus benthic. This information has important public consequences. It provides important parts of a puzzle that needs to be assembled and understood by stakeholders and decision makers alike. In listing the practices and concepts used in addressing this problem, there was one box unchecked: communication. Thank you, NBTI and U46 Science, for the opportunity to check that box. For the water chemistry and biology researchers or Excel teachers or global warming advocates, there are plenty of teaching opportunities buried in the data used for this presentation that will somehow soon, that we will somehow soon make available. You can see the sunrise and set as real-life photosynthesis is revealed in the patterns of temperature, pH, chlorophyll, and dissolved oxygen. The data on blue-green algae embedded in the spreadsheet has yet to be revealed. And the best part, there will be more data just like this in the future. So I should have just enough time to change the old film reels for today's second feature. We'll see you on the flip side. So the second case is a story not built with fresh data, but a new look at old data through the microscope of past practices and water pollution control. This case may be the scientific method in reverse. In my career, the scientific method has always been a two-way street, building and rebuilding hypotheses. If valid new contradictory data comes along, you have to correct your thinking. The case of the missing poison is actual real-life mystery that has defied mussel researchers for decades. The crime? Unexplained disappearances, including extirpation of our central Fox River Valley mussels. For one, Spike the mussel is missing, and it's our job to investigate. Mussels normally don't get much love. They hide themselves in the sand and gravel, sucking up and filtering out plankton and detritus for their food. Think of the mussels in our Fox as little Roombas, vacuum cleaners of the river bottom. Except they don't get around very well. That's Glute. Oh, that's Glute. He and his buddy QB will be hanging with us today. The venue of this case will be rivers of the United States. Similar unexplained losses of freshwater mussels at the end of the 20th century has been a problem seen throughout American waters. Let's meet the family. Freshwater mussels, native to our Fox, have a fascinating breeding routine. Mama mussels uses lures to trick fish into carrying her babies on their gills. The host fish nurtures those babies through adolescence to maturity, about 2 or 3 weeks. At that time, the tiny young mussels are fully formed and drop to the river bottoms, like young adults fresh out of high school. If the habitat is right, where the tiny mussels let go, they'll survive and maybe reproduce. At one time, mussels in our Fox had real economic value beyond the fact that they are free and very effective water filters. Let's go back in history to the year 1900. The Fox River used to be home to mussel populations so large, there was a freshwater pearl industry. Fox River mussel shells were valued for button making on an industrial scale. Glute, get out of, you're hiding the buttons. Get out of there. That's too weird. Since that time, mussel populations have crashed. Here's the mystery. If we look at mussel studies done in 1957, the blue bars, we see most places along the river have a dozen or so species. Except the central Fox River Valley between Algonquin and Yorkville, where mussel populations have crashed. The 1999 survey in red found no mussels at all in South Elgin, and St. Charles was down to a single remaining species. There were major losses everywhere over those 40 years, but the central Fox River Valley was a kill zone. A closer look at mussel species counts in the central Fox River Valley towns between Geneva and Aurora found major species losses over the 34-year period between 1969 and 2003. In the 2003 study, no live mussels were found at all in the 4 dam impoundments on this section of the river. Finally, mussel studies done in 2009 used the Mussel Community Index, the MCI, to characterize our river from McHenry at River Mile 98 to Weedron at River Mile 9. Once again, the 2 central Fox Valley sites in South Elgin and Geneva scored zeros. This is a mussel kill zone. So where did these mussels go and why are they missing? One problem we know is its mussels have limited mobility and need oxygenated water to survive. In the backwater pools behind our rivers' dams, there are problems with suffocating sediments and oxygen starvation. A little bit of sediment might not be great habitat, but it's okay for mature mussels maybe, but not so good for the recent graduates. Too much benthic sediment and the habitat is no longer livable. What is wrong in this section of the river near South Elgin or this section near Geneva? There has been a long history of muscular neglect in the disappearance of Spike and his clan. That's QB, he's Glute's buddy. Let me try to give you a graphic interpretation of recent mussel history. Nothing quantitative, just some important clues from the past. Let's get ourselves up to date. We'll call the year 1800 times zero. The Potawatomi Indians held the west bank of the Fox, and a few early settlers were on the east. Finest fishing in the land, everybody happy as clams. Around 1840, the Industrial Revolution hits the Fox River Valley. Dams are built up and down the river for water power. Mussel populations probably start faltering because of habitat loss. Around 1880, the Fox River Valley was growing and our Fox was a common sewer. Oxygen demanding organic waste shown here as CBOD, including ammonia, polluted the river and killed unknown numbers of mussels through asphyxiation and ammonia poisoning. By 1900, pearl and shell harvesting were part of the Fox River Valley economy. Overharvest may have caused additional mussel population losses. But by the 1930s, the mussel shell button industry was dead with the invention of plastic, and the mussel harvest of our Fox was over. Sewage treatment was commonplace and becoming effective at removing oxygen-demanding organic wastes, but ammonia was still an issue. By 2000, improvements in wastewater treatment had eliminated carbonaceous COBOD as an issue, and significantly less ammonia was being discharged, but mussel populations were still crashing. By 2010, ammonia discharges were a thing of the past, but by this time it was clear there was some reason other than habitat loss for the continuing mussel decline. Here is the mystery in a nutshell. By the 1980s, fish populations were responding well to improved water quality, yet Spike's family continued to be devastated. Kids, grandkids, cousins, nieces, nephews. What was happening to Spike and the other unionids? Disease is always a worthy suspect, but if disease were the cause, we would expect the disease to spread up into the Fox's tributaries, but that doesn't appear to be the case. The peak of the problem is in the main stem of the central Fox River Valley. How is that different from the northern and southern thirds of the watershed? Population density. The central third is by far the most densely populated section with a long history of sewage treatment. So, okay, aquatic gumshoes, let's summarize what we know. Our Fox's fishery has responded well to water quality improvements, but its mussels have not. Mussel habitat problems from dam construction and siltation still remain. There is no evidence of systemic mussel disease in river tributaries, and the highest mussel populations losses are in the central Fox Valley, where human population density has increased tenfold in the last 100 years. QB, get us the chloramine hypothesis. And then we need to learn some chemistry. The chloramine hypothesis. Chloramine has been responsible for unexplained unionid mussel poisoning since chlorine was first used for sewage disinfection early in the 20th century. Sewage treatment plants on our Fox began adding chlorine for disinfection sometime before 1920. When you add chlorine to water that contains ammonia, the two react instantly to form chloramine. Chloramine is widely used as a disinfectant in public water supplies. It's safe, effective, and lasts a long time. It lasts in water mains much longer than chlorine. So if chloramine is such a widely known chemical, it surely has to have been investigated and cleared of suspicion as a mussel poison, right? Did I mention that chloramine is used to kill zebra and quagga mussels? Zebra and quagga mussels aren't exactly like Spike and his family. For example, they don't take the adolescent school bus ride. But what we do know about chloramine toxicity but what do we know about chloramine toxicity to freshwater mussels like Spike? It turns out next to nothing. Criminals don't like to use their real identities, and chloramine has hidden behind a lot of aliases over the years. Mistaken identity appears at the core of this mystery, and that's important because of the confusion it has caused investigators. Chloramine has very different chemical properties than chlorine, but in the wastewater treatment business, the chemical name chloramine is almost unknown. Chloramine has always been referred to as some type of chlorine. Total chlorine, combined chlorine, chlorine residual are just a few. Chloramine has been measured and reported as chlorine since its first use over 100 years ago. If you listen carefully, I'll be making that very mistake in a couple of minutes. Find the error and receive extra credit. And if you want to find chloramine toxicity research on freshwater mussels, good luck. You can find tons of studies on chlorine toxicity to mussels and tons of studies about the toxicity of ammonia. But other than chloramine's use killing the invasive zebra and quagga mussels, interesting but not the same as Spike's family, I've found only a single study on freshwater mussels like Spike. Originally written as a master's thesis in the mid-1980s and subsequently published in 1993, Stephanie Goudreau's The Effects of Wastewater Treatment Plant Effluents on Freshwater Mollusks gives us the LC50 for Spike's cousin, the rainbow mussel. The 24-hour LC50 is the concentration of a poison found to kill 50% of the population tested in 24 hours. The chloramine LC50 for Spike's cousin rainbow is 0.084 milligrams per liter. And in this context, a small number is very big, telling us chloramine can be 10 times more toxic to mussels than ammonia. Glute, pay attention, this is important. To know if any chemical is effective, good or bad, you have to know how much is involved. In chemistry, concentration is key to performance. Chloramine isn't measured in the river, but we can do a quick estimating calculation to see if there's potential for chloramine levels in our fox to reach the killing concentration for the babies of Glute's cousin, the rainbow. During summer low flows, the fox at times runs through the central Fox River Valley at 200 million gallons per day. If City E, with an average treated sewage discharge of 20 million gallons per day, contains 2 milligrams per liter of chloramine, assuming full dilution, what would be the resulting bulk concentration of chloramine in the river? 0.2 milligrams per liter, 2.5 times the concentration lethal to baby rainbow mussel Glochidia. There are many variables in this kind of research, making the work quite challenging. Some species have more tolerance for certain chemicals than others. The toxic plume of chloramine from wastewater plants may be small for some species. But for chloramine intolerant species, the toxic plume would be much larger. This is the kind of plume we may have had for years on our fox. Some years with high river flows, the toxic plume disappears, not by magic, by dilution, only to reappear and kill again when river flows drop. We don't know how big these plumes can get or how long downstream they last, but we need to remember Spike's family tradition. Remember the young Glochidia, the nieces and nephews and grandkids? All have to take a 3-week adolescent gill ride to maturity. Even a small plume can impact baby spikes and rainbows and giant floaters taking their school buses, the bass, the catfish, the sunfish, to graduation. And the school bus ride inevitably would carry the glow kids into and out of the chloramine danger zone, killing the kids and ultimately their entire family in the central Fox River Valley. Chloramine is more persistent in the water environment than either ammonia or chlorine, and with one data point and circumstantial evidence, we suspect kills unionids, Spike's family, at a much lower concentration. And production of chloramine continually grew from its first introduction somewhere around 1917 through the end of the 20th century. And based on that production, it is possible, likely, that fatal concentrations of chloramine existed in our fox for many, many decades. And where the greatest concentrations of chloramine would have existed, the greatest mussel kill has occurred. This is the kill zone for Spike and his family. We've got a suspect, a known killer, hiding under multiple aliases that was on the scene while mussel populations plummeted. But we don't have anything except circumstantial evidence in a single reported toxicity study. Strong suspicion is often not good enough to convict. But with every good mystery, at the end, there's always a final twist that comes out of nowhere. Chloramine poisoning of our Fox River stopped in 2010. After nearly a century, chloramine poisoning or chloramine pollution finally stopped in the Fox River Valley with the last dechlorination retrofit of a wastewater treatment plant in 2010. Now, don't feel like you've been totally fooled by this final twist of the plot. As the title clearly stated up front, this is the case of the missing poison. If the chloramine hypothesis is correct, while there are still habitat issues with our dams and always the potential for disease, the mystery killer, chloramine, is gone, and our fox is ready to see the safe return of Spike and his family, the native unionid mussels. The Reverend Terry Gallagher of Aurora sent me this slide a couple of years ago, and it's really resonating today. My story is now your new story. There's a surprising cost of having lost our mussels and a cost to protect those mussels that remains. There are at least 4 paths to follow after hearing the story. 1, do nothing and let current practice stand. 2, support research into chloramine LC50s, extending Goutreau's work to Spike and other native mussel species. 3, bypass the research and collaborate to immediately repopulate the native mussels, now on the chance that the chloramine hypothesis is valid. Or 4, follow your own path of discovery into the world of science and engineering and the humanities, and hopefully a little enriched by this story. We're the Friends of the Fox River. We engage, we teach, we enjoy, and we thank you. But before we go, I want to give a shout out to a wonderful animated short produced by our friends in the Delaware River Basin. This is a wonderfully told 5-minute tale about the lives of our freshwater mussels. Thank you very much. And if there's time, I would be happy to take a couple of questions.
Thank you very much, Arthur. I enjoyed your CSI episodes. I do have some questions for you from the YouTube channel. One of the questions says, do rivers have a winter turnover like lakes do?
The Fox River does not, and generally rivers do not. The Fox River, most people have no idea what its depth is. They look down from the bridges that they pass over, and they don't know if it's 2 feet or 20 feet. The average depth of the Fox is about 2 to 4 feet. So temperatures are uniform throughout the year.
Okay, here's another question. Is it true that warm water releases oxygen and cold water takes in oxygen?
Oxygen solubility is dependent upon temperature, and warm water cannot hold as much oxygen as cold water can. Normally the temperature changes, though, are sufficiently slow so that you don't see any release. But sometimes in the wintertime, here at my home in Elgin, If you turn on the cold water tap, it'll look very, very cloudy because of the dissolved gas in it. But as it warms, it will clear. So that's kind of a kitchen science test that you can do with oxygen and gas solubility at different temperatures.
Thank you. When did you first become interested in studying the Fox River, and what triggered your interest?
Oh, that's a terrific question. I suspect it goes back to when I was a kid, probably 5 or 6 years old, and my dad. I lived in Lombard, and my dad took us up fishing in the Fox chain of lakes. It probably took me well, an entire career to get back to really to the Fox. So I've been working with friends of the Fox River, looking at these issues of the river for the past 3 or 4 years. But that's in addition to nearly a 50-year career in sanitary engineering, water pollution control, and public water supply.
Thank you. Do you have a favorite spot along the Fox River that you like to go to?
I really love the section of the Fox north of the Carpentersville Dam up towards Wisconsin. It has good free-flowing waters. The Carpentersville Dam hopefully will be removed in the next couple of years and provide much better free-flowing river sports and a better aquatic environment and better fishing all around. So I would say up north, but there are lots of different places along the Fox that people enjoy.
Thank you. As a science educator, as I listen to you talk, I enjoyed listening to you talk about models, because that's one of the science and engineering practices that we are trying to involve our students in. And I was very interested to see that you hit on many of the science and engineering practices that we cover, as well as the cross-cutting concepts. I think cause and effect is one of the cross-cutting concepts that is a big part of your work. Is that true?
Very much so.
And also stability and change seems to be another one that is important in your work.
Every day.
Do we have any more questions for Arthur? You can put a question in the Q&A if you would like. What can we, as everyday citizens that live in the Fox Valley area, what can we do to support the work in the Fox River?
Well, you can join the Friends of the Fox River. If I can still share my screen, or
Sure.
you might be seeing.
It's yes, it's there.
Yeah. Mm-hmm. If you just click on that QC code, that will take you right to the Friends of the Fox River website, where we're a lot of different people do a lot of different good things, talking and learning about the Fox River, and we'd love to have you join us. And there's a special student discount membership, I understand.
Great. Well, we thank you very much for taking the time to come and share with us today. We have enjoyed your CSI episodes. Thank you very much.
Thank you. Bye-bye.
Bye-bye.